Hello everyone, welcome to this lecture. So, we will continue our discussion regarding the ABY conversions. We had already seen few conversions in the last couple of lectures. So, in this lecture we will consider the conversion from the Boolean sharing to the arithmetic sharing, and we will see two conversions for this category, one which requires a constant number of rounds and one which requires a non-constant number of rounds. Okay. So, just to quickly recap, we are currently looking into the conversions between three different secret sharing semantics for the two party case: arithmetic sharing, Boolean sharing and a Yao sharing. We had already seen few of these conversions. Now, we want to see the Boolean to arithmetic conversion B to A. So, the input for this conversion is as follows. You have L bit number which I call as Z, whose binary representation is Z0, Z1, ZL minus 1 from LSB to MSB. Each of those bits are Boolean shared as per the GMW secret sharing semantic. Okay. And what is the output that we want from this conversion? We want the two parties to now possess arithmetic shares, namely two L bit numbers, such that if we add those two L bit numbers modulo 2 power L, the output is equal to Z, or the value is equal to Z. And in this whole process the value Z should remain private. Okay. That is what we want here. So, let us see option number 1 to do this conversion, and the idea behind this option number 1 is as follows. We will ask one of these two parties, say P naught, to pick a random L bit number L r, and our goal will be to ensure that Bob or the other party should obtain the value Z minus r, and Alice can keep r as her share for Z. So, Alice will keep r as her share for Z, Bob will keep Z minus r as his share of Z, and you can see if we add r and Z minus r, the output will be Z, and in this whole process the value of Z should remain private. That means, Alice, even though she is picking r, she should not learn the value of Z, but somehow the value Z minus r should be given to Bob through some protocol. So, how it is going to be ensured? This is ensured as follows. So, imagine you have an L bit Boolean circuit, and this L bit Boolean circuit takes inputs both from Alice as well as from Bob. The inputs of Alice are her GMW shares for the bits of Z. Okay. So, she has her GMW shares for the bits of Z. So, they constitute one set of inputs from Alice, and apart from that it also takes the random number, the bits of the random number r picked by Alice also as the input. Okay. So, Alice has two sets of input, 2L inputs here for this circuit, and the input from Bob's side for this circuit are Bob's GMW shares for the bits of Z. Okay. So, Bob has his GMW shares. So, this L bit Boolean circuit takes those shares as inputs from Bob. And what is the output of this Boolean circuit? The output of this Boolean circuit is the value Z minus r only for Bob. That means, the output of this circuit is not going to be available both to Alice as well as Bob. The output will be only for Bob, namely for the party who is not selecting the value r. Okay. Because if Z minus r is also given as an output to Alice, and then since she has anyhow r, she will learn Z in the process. So, we require here a Boolean circuit which, when given these bits, namely the Yao shares of Z from Alice and Bob and the bits of r, the circuit should produce the output Z minus r for Bob. Okay. So, you can easily imagine what exactly that Boolean circuit will look like. The Boolean circuit, the internal logic of this Boolean circuit will be as follows. It will first construct the bits of Z by XORing the GMW shares of bits of Alice and Bob, which are fed as input to this circuit. And once it computes the bits of Z, it will know the value Z, and then it has to basically add the bits of Z and the bits of R and produce the output Z minus R for Bob. That is what is the internal logic for this Boolean circuit. Now, the idea behind this B to A conversion is to let the two parties, Alice and Bob, securely evaluate this circuit. Okay. And to securely evaluate this circuit, what Alice is going to do is she is going to share her parts of the inputs for this circuit by acting as a dealer. Okay. So, she will be doing the GMW secret sharing protocol. So, she will act as a dealer and secret share each of her shares for the bits of Z, and she will also act as dealer and secret share the bits of R. And what Bob is going to do is Bob is going to act as a dealer and he is going to secret share his inputs for this Boolean circuit. So, his inputs are his GMW shares for the bits of Z. So, he is going to act as a dealer and secret share those bits. And now, the inputs for this Boolean circuit are made available to these two parties in a secret shared fashion. What they are now going to do is they are going to evaluate this circuit over the shares of the inputs as per the GMW circuit evaluation process. Okay. So, I am calling this circuit as CKT. Okay. Now, once their inputs, so you can imagine that this is a Boolean circuit which will have XOR gates and AND gates. What I am saying here is that now Alice and Bob both will interact and evaluate each and every gate of this circuit CKT and reconstruct the output Z minus R towards Bob. If this is done, then the arithmetic share for Alice will be R and the arithmetic share for Bob will be Z minus R. And in this whole process, the privacy of Z is maintained because neither Alice disclose anything about her GMW shares for the bits of Z because they are secret shared, and in the same way Bob also does not reveal anything about his GMW shares of Z because he has secret shared. Okay. So, that is option number 1 here. So, in this option, in this conversion from Boolean to arithmetic sharing, the communication overhead is less, communication is less, but number of rounds is not constant. So, why the number of rounds is not constant? Because if we go into the internal logic of this circuit CKT, then its multiplicative depth will be proportional to L, and hence by multiplicative depth I mean there will be the number of layers of AND gate, the independent layers of AND gate, and for each layer of AND gate the parties need to interact and the number of layers of AND gate will be proportional to L. So, that is why the number of rounds required here to do this conversion will not be a constant, it will depend on the value of L. So, if your L is large, then it will require a large amount of interaction among the parties, but during those interaction the communication will be less. So, if you are fine to allow the two parties interact, that means if the network latency is not very bad, then you can go for this conversion because the communication wise this conversion is very efficient. Now, let us see the other option of doing the Boolean to arithmetic conversion, where we will now require a constant number of rounds, and now you can immediately think that okay, since we are aiming for constant number of rounds, somewhere we have to either bring in oblivious transfer or we have to somehow invoke Yau's, we have to evaluate some circuit in according to Yau's protocol. Okay. These are the only options. So, this option number 2 for doing the Boolean to arithmetic conversion goes as follows. So, imagine the value z which we want to be secret shared has its bits z naught from LSB to MSB z naught z 1 z I z L minus 1. Okay. Neither Alice nor Bob knows the exact values of these bits because they have GMW shares of these bits. Now, since z is an L bit number and the bits of z are z naught to z L minus 1, I can write z as per this formula. So, I take z naught multiply with 2 power 0, z add and all the way to z I 2 power I and all the way to z L minus 1 2 L minus 1 2 power L minus 1. Okay. Now, this z naught can be expressed as the XOR of the GMW shares of z naught available with Alice and Bob, and outside you have 2 power 0. In the same way, if I consider the term zi, zi can be expressed as the XOR of the GMW shares of zi available with Alice and Bob, and outside you will have 2 power I. And in the same way, ZL minus 1 can be expressed as the XOR of the GMW shares of ZL minus 1 available with Alice and Bob, and outside you have 2 power L minus 1. Okay. And now, let us look closely into each term here. So, if I consider this first term I can rewrite as I subtract R naught from this first term and add R naught to the first term. So, since I am subtracting R naught and adding R naught, the effect of R naught is not there, hence basically I am getting the first term only. So, I am not changing the contribution of the first term here. So, here R naught is some random L bit number. And the same thing I do for each and every term. If I consider the last term, I can rewrite this last term as if I take the last term, subtract a random L bit number and add the same L bit number. Okay. So, this R naught, R 1, R L minus 1 are random L bit numbers. The idea here is each of these terms can be rewritten as I mask it. I mask each term with a random L bit number and unmask it with a random L bit number, the masked value. So, the effect of masking is not there. Now, our goal is to ensure that at the end of this Boolean to arithmetic conversion for this L bit number z, we should have 2 L bit numbers, one part held by Alice, another part held by Bob. So, that if we sum those two parts, we get the number z. That is what we have to do. Now, if we look closely here, what we can do is the following. We can ask Alice to pick all this L bit random number. So, we can ask Alice to pick R naught, R 1, R L minus 1. Let Alice pick all these values. And now, within each of this within each curly bracket, if we somehow ensure that the masking of the terms with the corresponding R values go to Bob somehow. That means, if I take the first curly bracket here, then somehow we ensure that Bob gets z times 2 power 0 minus R naught. From the second curly bracket, Bob gets z 1 times 2 power 1 minus R 1, and like that from the last curly bracket somehow we ensure that Bob gets z L minus 1 times 2 power L minus 1 minus of R L minus 1. If we ensure that Bob gets these terms, then we have actually identified the arithmetic shares of Alice and Bob here. Alice can keep her arithmetic shares to be the summation of all these random R values, and within each curly bracket whatever portion we are ensuring Bob receives, if Bob sums all those pieces, then that constitutes Bob's share for the number z. And now you can see that indeed if we sum Alice's share and Bob's share, we indeed end up getting the value z. That is the idea behind this conversion. Now, everything boils down that how within each curly bracket this masked thing gets transferred to Bob, and in the process nothing about Alice share of the Alice GMW share is learnt, and in the same way nothing about Bob's GMW shares for the bits of Z is learnt. That is what we have to ensure. Okay. So, let us see how exactly the ith term, the masking of the ith term that we are desiring here gets transferred to Bob. Okay. So, you can imagine that Alice and Bob participates in LOT instances. I am going to show you only the ith OT instance, because you can imagine that in the same way the parties Alice and Bob are actually executing LOT instances. I am just going to show you the inputs with which they participate in the ith OT instance. So, in the ith OT instance, Bob participates as a receiver, with his choice bit being the GMW share for the bit Zi. Okay. And our goal is to ensure that at the end of the OT instance, Bob should get Zi times 2 power I minus Ri, where Ri is a random value picked by Alice. So, in this process nothing about Zi is learnt by Bob, because Ri is a random value and Zi times 2 power I is masked with Ri. So, that preserves the privacy of the term Ci. Now, to ensure that Bob indeed receives this output through the OT instance, Alice will participate as sender with her message M0 and M1 being these values. So, M0 will be her GMW share for the bit Zi times 2 power I minus Ri, and M1 will be the complement of her GMW share for Zi times 2 power I minus Ri, where Ri is a random number, L bit number picked by Alice. So, now you can check that indeed if Alice participates with these values of M0 and M1 and Bob participates with this value of selection bit, then from the correctness of the OT, Bob will receive this output. Okay. Say for instance, Bob's GMW share is for the bit Zi is 0. If it is 0, then he should get the message M0. So, if his GMW share for Zi is 0, then the XOR of his GMW share and Alice GMW share will give actually Alice GMW share, and outside you have 2 power I minus Ri, and that is precisely is the message M0. Whereas, if Bob's GMW share for Zi is 1, then he should get the message M1, and indeed if his GMW share is for the bit Zi is 1, then the XOR of these two terms will be the complement of Alice share for the Alice's GMW share for the bit Zi times 2 power I minus Ri. Okay. So, you can imagine that this OT instance is with respect to the ith term. Since there are L terms here, you can imagine that Alice and Bob participates in L independent OT instances. For each of the OT instances, the random value Ri's are not the corresponding random value Ri is picked uniformly at random by Alice, and that ensures that even though Bob receives through the ith OT instance Zi times 2 power I minus Ri, since Ri's are acting as a mask and they are picked independently of each other, nothing about the exact value of Zi is learned in the process. Okay. And the privacy of receiver in this case ensures that through the in the OT instances nothing about the GMW shares of Bob are learnt by Alice. Okay. So, that is a constant round conversion. Why constant round conversion? Because all these OT instances can be executed in parallel, and OTs require a constant number of round, but OTs require us to perform public key operations, but we can take the help of OT extensions, namely all the B2A instances for which conversions are required during the computation, Alice and Bob can do the following. They will identify that okay, at these points we have to do the B to A conversions. So, they will identify the number of B to A conversions that are required. Say if it is L, capital L, then they can do the small l times capital L number of OT pre-processing, and then later when the exact OTs are required, they can perform only symmetric key operations and do the corresponding B to A conversions. So, that way this requires a constant number of rounds of interaction. So, these are the references used in today's lecture to discuss the B to A conversions. Thank you.